we considered the control volume for the one-dimensional heat conduction problem, including convection. So there's a heat flux which takes place in the x direction, and of course there is heat convection taking place, let's say, in other directions. Let's say we can call it QH. We can also think of this as, let's say, of a problem where a bulk, a solid bulk, a solid, let's say, block is insulated in all three sides and exposed to a free stream on the right hand side, or in the free end. So the temperature of the whatever the fluid which is exposed to can be written as T infinity. And since all the boundaries are isolated or insulated throughout the other three, these three surfaces, there will be no heat transfer taking place. So there will be a convective heat transfer from this solid interface to the liquid at this free end. Having this in the mind, we can go back to, let's say, the original energy balance equation. We can write the conservation of energy again for this particular problem by applying conservation of energy. We can write the heat, the energy corresponding to the heat flux, input heat flux, that is Qx multiplied by the area times, multiplied by the time. When we think of the heat generated in the system, capital Q multiplied by the volume times the time. The change of the stored energy, which can be obtained by multiplying the heat capacity, specific heat capacity, the mass of the system, that is the density, multiplied by the volume times the temperature difference, and the exit, the flux at the exit point, x plus dx, area multiplied by the area multiplied by the time. In addition, now we see a convective term, the convective heat flux times P, which is given, P stands for the perimeter, times dx times dt. All the terms are the same as it was the case for the one-dimensional heat conduction problem. But in addition, we have introduced another term for convection, which is given by QH, simple QH times heat. Convective heat transfer can be defined using the Newton's cooling law, where QH can be written as the heat transfer coefficient between the solid to liquid interface with and the difference of the temperature of the surface and that of the free stream. You are quite familiar with these equations. Yeah, so the heat transfer coefficient has the units of, let's say, kilowatt per meter squared per Kelvin or per Celsius degree. And of course, T is the temperature of, let's say, solid to fluid interface, and T infinity is the temperature of the fluid. In this equation, in equation 9.2.1, P defines the perimeter around the constant cross-sectional area. Yeah, so the heat transfer, amount of heat transfer is defined by unit length, so it has to be multiplied by the perimeter to obtain, let's say, the overall heat transfer corresponding to that cross-sectional area. So again, using the previous equations which we derived in the first section, that is, we can use equations 9.13 to 9.16, and also the one which we just derived, 9.2.2, and substitute all these in equation 9.2.1, which is the energy balance equation, because we already have these definitions or expressions for these equations, which we derived from the previous section, and also by dividing it by a particular term. So Then we can, after certain simplification, we can obtain the one-dimensional heat conduction with convection. Can be written as, again, the partial derivative times the thermal conductivity of a partial derivative of this term and the heat source, the corresponding terms with respect to the change of the energy, the stored energy, and additionally we have a new term corresponding to convective heat transfer coefficient or convective heat transfer process. Just like in the previous case, we can apply the proper boundary conditions. If the temperatures are known, temperature gradient can be calculated, then the convection can be found. Convection heat transfer coefficient can be found in if the temperature of the solid to surface interface as well as the free streams are known. We can also further write by further simplifying this problem. Let's say if we consider this scenario by equating, let's say, the heat flow which takes place in the bulk to the heat transferred via the convective process, heat conduction in the bulk and heat convection in the free stream. If we equate this at the surface, let's say at surface 3, we can simply write down this equation by equating, let's say, heat flow. So in solid wall to heat flow in the fluid stream, or let's say solid to fluid interface, we can write the convective conduction heat transfer. The heat transferred by conduction is equal to the heat transfer by the convective process. This is at surface 3. On that note, we have, let's say, now you must have recollected the fundamental concepts or physical phenomena with respect to heat conduction and heat convection in one-dimensional as well as two-dimensional problems. Next, let's try to now, since we have already got some kind of foundation with respect to the heat conduction and convection process in one dimension, two dimensional, let's try to go ahead with the finite element formulation of this heat transfer problem. And before that, let's quickly get familiarized, because I have seen often the students get confused or let's say do mistakes because they get the units wrong. So just quickly recollect 9.3 to recollect the units used in heat transfer problems. Yeah, so the typical units, you can either use, let's say, SI units or also imperial units. If we think of, let's say, different terms and the corresponding SI units and the imperial units, let's say US customary, and define the physical entity here. The thermal conductivity, which is defined by capital K, has the units kilowatt per meter per Kelvin or per Celsius degrees. So we if we are to use US customary units, it's BTU per hour times feet per Fahrenheit degrees. So often they use these imperial units for their representations. The temperature, of course, it's either Celsius degrees or Kelvin in terms of SI, and it's Fahrenheit usually in customary units. For internal heat source, which is heat stored per unit volume, let's say per unit time, that is kilowatt per cubic meter. In imperial units, BTU per hour feet cube. Heat flux Q is kilowatt per square meter. Similarly, BTU per hour times feet squared. The heat transfer coefficient, the convection heat transfer coefficient given by H is has the units kilowatt per meter squared per Celsius degree or Kelvin. It's BTU per hour feet squared per Fahrenheit degree. So the energy is kilowatt per hour. Here it's BTU, British thermal units. Specific heat C is kilowatt per hour per kilogram per Celsius degree. British thermal units per slug Fahrenheit degree. Finally, how about the mass density? Rho is given by kilogram per cubic meter in SI units and slug per cubic feet in terms of the British or imperial unit. So yes, based on this, let's try to now, because we will be tackling problems maybe also using SI units as well as imperial units. So that's the intention of getting familiarized with these different types of units, and for your information, not to make a mistake when you use these units. And of course, when you write out the equation, if certain quantities are missing, you can easily identify because you're already aware of the units now. So on that note, let's try to start with, let's say, the finite element formulation of a 1D heat transfer problem. Let's say 1D finite element formulation using variational method. This is nothing new. We are following the same steps as before, the same 7 or 8 odd steps that we used for tackling structural problems. The only difference in this case that is the application. The properties, the material properties now include not modulus of elasticity or Poisson's ratio. In this case, it includes, let's say, thermal conductivity and heat transfer coefficients. We are not dealing with strains or displacements in this problem. We are dealing with temperature gradients. And the inputs, or let's say the forces applied, are not, let's say, actual forces. The analogous forces applied in heat transfer problems are heat fluxes. That is the analogy. So it is the same thing, it's just different physical quantities. So we will not go into detailed derivation, but I will only highlight the important aspects so that we can, it will be more interesting to work out the problem, since we have already derived the corresponding underlying equation, and it's a matter of changing the, let's say, physical entity, and the problem or the methodology would be the same. So as we know, by modeling a problem using a finite element method, by modeling a heat transfer problem using a finite element method, our intention is to find a heat distribution, or let's say temperature distribution, within a certain body, provided that it is subjected to certain heat fluxes and, let's say, certain boundary conditions. We are interested in finding the temperature within a certain element or within a certain body. Keeping this in mind, let's go through these typical 6 processes that we used in our structural problems for deriving the stiffness matrices for obtaining the strains and, of course, stresses and the forces in structural problems. So step 1 is to select an element type. So in this case, let's consider a basic element, basic line element having 2 nodes. Let's consider line element having 2 nodes. Let's name them as 1 and 2. The line element has a length of L, and we are interested in 1D heat transfer problem, the local coordinate system, x hat. The temperature at node 1 is T1, temperature at node 2 is T2. And now, since we are tackling a one-dimensional temperature element, then we are now interested in, as the next step, of course, we are interested in defining a shape function, yeah, or a temperature function. What does a shape function or temperature function tell us? How the temperature, it tells us how the temperature varies within a certain element. This is the element that we have considered here. We make a simple approximation that the temperature within the element changes in a linear manner. This is the simple approximation that we make. So at node number 1, we assume a temperature to be T1. At node number 2, we assume the temperature to be T2. And along the element, there will be a variation in temperature, which can be defined using the shape functions. This variation, let's write the temperature along the length is T, can be obtained by write it like this: N1 T1 times N2 T2. Simple linear variation of the temperature. Okay, this is step 2. Selecting a temperature function. Temperature at any point along the length x can be obtained. Let's assume a simple linear equation, yeah, N1 T1, N2 times T2. So here T1 and T2 are the nominal temperatures which we will like to obtain, and we can define N1 and N2, which are the shape functions, in this manner, such that when the x-hat coordinate is equal to 0, that is corresponding to node number 1, at node number 1, the shape function would be equal to 1. Similarly, we define N2 such that the corresponding shape function is 1 at x-hat is equal to L. This is just like in the previous case that we used for defining the displacement within the element. So in the matrix form, now we can write the shape functions in the form of a matrix. N1 is 1 minus x-hat divided by L, and N2 is x-hat divided by L. So the nodal temperature matrix can be written as, we have two nodes in this one-dimensional heat transfer problem. Temperature at node 1 and temperature at node 2 can be written as a column matrix and represented in using equation 9.44. So in the matrix form, we can now relate, let's say, the equivalent in structural problems. What did you use? We used force, the total force applied is equal to the stiffness matrix times the displacement. In this case, the temperature, let's say, applied on the system, so to say, the shape functions times the temperatures. So what we have done is we have simply used this, written this equation 9.4.1 in the form of matrix. You can separate this into two matrices. It's clear, isn't it? So next step is to, in step 3, we introduce the displacement, the strain and the stress strain relationships and stress displacement relationships. In heat transfer problems, what we do is we introduce temperature gradient and temperature heat flux relations. We define temperature gradient and temperature and heat flux relations, or temperature gradient relationships. So if you can recollect the strain matrix, yeah, the strain matrix, which was defined by epsilon, was written with the help of, let's say, a so-called B matrix and unit displacement. So similarly, we can write the temperature gradient matrix in heat transfer problems, temperature gradient matrix G, where G is equal to nothing but the temperature gradient. And this temperature gradient, something like the strain in the case of, let's say, structural problems. If you can recollect, we wrote the strain with the help of a B matrix and unit displacement. In this case, we use a B matrix, and then we have to use the corresponding input for the system or unknowns, which we would like to determine is the temperature of the nodes. Okay, so here B can be simply obtained by using this equation 9.41. What is 9.41? This equation 9.41, we can use this equation and differentiate this equation with respect to dx hat. We can differentiate this equation with respect to dx hat to obtain the B matrix. Differentiation with respect to equation 9.4.1, this equation with respect to x hat, you would obtain an equation or relation for B matrix, which I will directly write down. So we can differentiate this first shape function n1 with respect to x hat, and differentiate again 2 with respect to x hat. This is the form you would get for the B matrix. So using the definitions of B and using equation, let's say the second equation which we derived, since we have expressions for n1 and n2, we can differentiate n1 and n2 with respect to x and write down the expressions. The B equation would be 1 over L over 1 over L, minus 1 over L or 1 over L. Right, we have an equation for, or we have an expression for B matrix. Then the heat flux or temperature gradient relationships can be written using the constitutive matrix. Heat flux is proportional to, let's say, the temperature gradient given by the G matrix here, the temperature gradient matrix, and the proportionality constant in this case, if it is a 1D problem, of course, if it is an element, we consider them to be thermal conductivity. In this case, if we would like to consider an element which contains 2 nodes, it is the constitutive matrix, since we are dealing with matrices now. If you can recollect this, the constitutive matrix, when it comes to plane stress and plane strain problems, included Poisson's ratio and these different such terms. Yeah, so here the material properties gets included. So the material property matrix in the case of one-dimensional problem, the constitutive matrix would be simply the thermal conductivity. These are the basic equations that we would like to use for deriving the stiffness matrix for a one-dimensional heat transfer problem, or for an element which can be used for one-dimensional heat transfer problem. There's a lengthy derivation since we have already dealt with this similar derivation in the case of structural problems. I will not go let's say with the derivation in the next step, derivation of element conduction matrix and equation. So I will leave this part up to you if you are interested. So in this particular type of derivation, it is more convenient to use an energy minimization approach, which of course we did not cover. What we do is we try to calculate the total potential energy, or in this case, the total energy of this system, and we try to minimize it and try to obtain expressions for the different, let's say, the forces applied into the system. And of course, after lengthy derivation, we can conveniently arrive at an expression for the stiffness matrix for a heat transfer, which can be used in a heat transfer problem. So by skipping, let's say, a lot of steps, I will simply write down, let's say, the results which we would obtain and which we would like to use in the examples that we would like to tackle. Okay, so if you do the derivations correctly, this is quite, you will see, and also an analogy between the structural and non-structural problem. The stiffness matrix you would get for analogous heat transfer problem is simply A times Kxx divided by L, and for this particular element is a symmetric matrix. The off diagonal terms are -1. So A refers to the cross-sectional area, L refers to the length of the element, KXX refers to the thermal conductivity in this X direction. Yeah. So this is the equation or the stiffness matrix for conduction part. And if there's a convection part included, of course, then there will be an additional, let's say, the stiffness matrix for this particular element would have the form H times P L divided by 6 2 2. So H refers to the heat transfer coefficient. Since we are convective heat transfer coefficient at the solid to fluid interface, P stands for the perimeter, L the length of the element. So here, so in this case, of course, we assume the perimeter to be constant. So the total matrix where we have a problem of conduction and also convection for a particular element, the total stiffness matrix, or the K matrix, can be written as a summation of the conduction term and a convection term. Okay. So whenever there's a, of course, whenever they are in the absence of a convection heat transfer coefficient or convection heat transfer, if we have insulated boundaries, then we can eliminate the second term and only the conduction component will be present. Yeah. So since we have already dealt with, let's say, the stiffness matrices, the equivalent matrices for heat transfer problem, conduction and convective heat transfer problem, the next what is remaining is the equivalent force matrix. So the equivalent force matrix, I will also directly write down the equations so that you can directly use them in performing the calculations in the exam, as well as within the, I will, let's say when you're working out the problem, I will give you directly the equations so that you can directly use them. You don't have to memorize these equations. So when we think of, let's say, the force terms, that is now, if you can recollect, yeah, in the case of structural problems, we always use this type of formation. Yeah. So this part in the thermal problem, we have already defined it, derived. We know in the case of thermal problem, we are not interested in an unknown displacement. We are interested in calculating the unknown temperatures at nodes. And what are the corresponding forces which is caused due to the fluxes, the heat generated, the fluxes which come due to, let's say, the input flux and the output flux, and the fluxes due to convective heat transfer. Such effects should be included, such boundary conditions should be applied. So what are the fluxes which we have to deal with when we talk about the force matrix? We have to deal with, let's say, the fluxes which are corresponding for generation of heat. Let's call it FQ, which can be obtained by, let's say, with this equation. I will directly write down the equation here. Shape function transpose multiplied by the heat. If we assume the generated heat to be constant, of course, Q times dV, and this is a volume integral if you are interested in calculating the total flux, so total corresponding force element due to the generation of heat. And if you assume the heat generated to be constant, we can take the Q term and write the area, the volume, as a multiplication of, let's say, area times dx hat. Yeah. we can write down this matrix, or Q. We can take Q term, the heat generated, and the cross-sectional area out of this integral, yeah, and perform the integral only at the length from 0 to L. And now the shape function, of course, would correspond to n1 will correspond to 1 minus x hat divided by L, and n2 will correspond to x hat divided by L dx hat. So by simplifying, we will be able to obtain an equation for this force corresponding force matrix. So let's call this 9.410. Similarly, what if we consider the heat fluxes, the corresponding forces, equivalent forces generated due to, let's say which we have to apply when we consider heat fluxes. So the heat flux is obtained by multiplying by the transpose of the shape function, and it is a surface integral because it takes place over a surface, the heat flux over a surface. Now we can assume the heat flux to be constant, take it outside the integral. P stands for the perimeter. Now perform the integral from 0 to L, and the corresponding shape function matrix can be written in this way. So I will directly write down this by skipping a lot of, let's say, derivation section, and you will have to directly use this. And this part will be clear when we do the examples. And what if there's a convective term? Yeah, if there's a convective term, then we can write the corresponding force matrix to be, again, the convection takes place over a surface. Let's call it over surface 3, which is defined by h times the infinity multiplied by the shape function times ds, that is over the surface, which would yield this formation. The corresponding term or force matrix if we are to deal with convection of a heat transfer component. So let's say, and another point which we would like to discuss before moving on, let's say, what if there's a free end? Yeah, this is the convective part where the convection takes place, of course, to outer surfaces when there are two elements which are in contact with each other. So before we move on to an example, finally, let's say, I would like to highlight, what if there's a free convection from an end of an element? Assume that there's an element like this. So the convection at the free end would be quite different if we assume the fluid flow at the of the fluid to be T infinity. We can write down, let's say, the convection at the free end using, let's say, we can define the corresponding stiffness matrix for this free end term by evaluating the surface, perform the integral at the surface using these equations. We know at, let's say, in this case, at node number 2, the shape function corresponding to n1, of course, n1 would be 0 and n2 would be equal to 1, because we are evaluating this integral at the very right end, since we want to obtain a stiffness matrix for the free end heat convection problem. So heat convection at the end would be, it's nothing but convective heat transfer coefficient multiplied by the area and corresponding matrix. So don't worry, this will be clear when we do an example. Yeah. because this is I've skipped a lot of steps to write down these steps. Without these steps, the picture won't be complete. So that is why I wanted to write down these equations so that you can directly follow. And the corresponding, let's say, the force, convective force, can be written down using this term, n times n2. Since we are interested in calculating it at the free end, we know T infinity times A. This would correspond to n1 would be 0, n2 would be 1, the free end. Okay, let's call it equation 9.4.17. Now we have, we have seen, I have mentioned the stiffness matrices corresponding to conduction, convection, and if there's a free convection term, what are the stiffness matrices or K matrices that we have to use, and what are the force matrices we have to use in convection and heat generation, and of course, if there's a free convection at the end, what are the force terms that we would like to apply. As we know, in the next step, it's all about assembling the matrix, assemble the element equation. So to construct the total structure stiffness matrix, and of course, then to apply the boundary conditions and solve the unknowns. This is what is remaining. The step is assembling. Step 5 is assembling the element equations. And of course, then construct the total structure stiffness matrix, then of course, then introduce boundary conditions, then solve for the unknowns. You can solve for the nodal temperatures and of course, temperature gradients and of course, heat fluxes, so on and so forth in an element level. Now we can start with an example. Let's do several examples to get familiarized with this setup, or how to use a finite element method in the heat transfer problems. Then it will be more clear to you. You will see it's quite simple transfer to apply or to select the proper stiffness matrix corresponding to a certain element, and of course, properly select the force matrix. And after you construct the element stiffness matrices, you can use the direct stiffness method to construct the total structure stiffness matrix for the problem and then solve for the unknowns. It is the same thing that you did all around through this course. Only different is the application.